And we're ready to go. Okay, so thanks very much everyone for coming. I'm sorry we're starting a little bit late. Let me introduce myself. I'm Alistair Jones. I work at Neo4j. I've done that for over 10 years. I live in London. In my job at Neo4j, I manage some of the engineering teams, and I also do architecture for Neo4j Aura. So what is Neo4j Aura? Well, as we say on the website, it's fast, scalable, always on, fully automated, fully managed graph platform offered as a cloud service. We have two flavors of Aura. For developers who are building applications, we have Neo4j Aura DB. For data scientists who are doing graph analytics, we have Neo4j Aura DS. Now, let's talk about what it means to be fully managed. If you want to run a database in the cloud, I think you need to think about at least these 5 things. So first of all, you need some servers to run it on. You need some server infrastructure. You probably need some kind of clustering or some means of assuring availability. You need to be able to upgrade the software, the database software, to take bug fixes or security patches. You probably want to adjust to different levels of load. So you're going to need the ability to scale, to change the size of the hardware that you're running on. And finally, you need backups. You need some way to be able to go back in time in case you delete your data for some reason. You need to plan that. If you self-manage this in the cloud, you need to worry about all these things, and that's why I've colored them grey. None of them are done for you, but you can get these managed for you. So the next level up I've got on this picture is to do something I've called platform managed, and what I mean here is something like the Helm charts that my colleagues Bleddy and Harshit were talking about earlier today. That's great because then you can run on one of the managed Kubernetes services, and it will sort out the server infrastructure for you using the Helm charts. It'll also do the clustering for you, but it's not going to solve the other things at this stage. It won't do the upgrade, it won't do the scaling, it won't do the backups. If you want all those things taken care of, then you're in the fully managed service realm. And that's where we are with Neo4j Aura. Now, for this talk, it's how we built Neo4j Aura. And what I mean by that, what I'm going to talk about is the time period from 2017, roughly when we kicked off the project in earnest, to now, so about 5 years. I'm going to start off with a little recap of where we were before we started the project. At the end, there'll be a glimpse of the future, like what's coming next. So before, back in 2017, we already had the world's leading graph database. We had people all around the world with all sorts of use cases using Neo4j really widely. And the vast majority of them were running in the cloud back then. You could probably say 10 years already at that point that Neo4j had been running in the cloud. So we knew it was possible. We knew it was possible to offer this service, obviously. And then as Emma was talking about this morning, we also had a really strong engineering team. We had the graph database experts in our staff. So facing the project, facing us was a number of challenges. And this is how I remember it anyway, that we were looking to support tens of thousands of production databases. Since they were production, we need to ensure uptime and availability. We're going to want to run them on multiple clouds because we could see that was going to be a long-term direction. We could already predict that customers are going to have slightly different needs based on the type of use case that they had. And finally, we need to design systems so that we could keep on evolving it. We could keep on developing it to add all the new features that we could see coming into the future. I don't know why it's starting. So the way that we chose to address all these challenges, I've had it as three core principles. So first of all, it's about using the best cloud infrastructure. So we want to run in the best way that we can in the cloud, use the best capabilities of the cloud that are available. But we don't want to build everything ourselves, so sometimes we're also going to use the best third-party services that are available to do our non-core capabilities. And finally, the way that we organize and the way that we work, we want that to use the best possible practices, to think about the structure that we use in the team and the process that we follow. So I'm going to go through each of those in turn. First of all, we'll look at the cloud infrastructure. Now, the big news, the first thing to say is the multi-cloud. I already touched on that. And right now, Aura is running on AWS, on GCP, and coming soon on Azure. And why do we do that? Well, it's because of customers. We know that there are customers who use these clouds. They've chosen for whatever reason that they want to be on those clouds, and they want us to meet them there on those cloud platforms. And that's why we're in that realm. Now, the big story here is Kubernetes. So I'm sure everyone has heard of Kubernetes, at least. We've chosen to build Aura on Kubernetes. And that's a conscious decision for us. And I'm calling it a Kubernetes opportunity. So at the top of this picture, I'm trying to show how some of the other database as a service offerings operate. And there are other database as a service offerings out there. And especially if they started before Kubernetes was available, they run on these lower level pieces of cloud infrastructure. So virtual machines, that was the canonical graph piece of cloud infrastructure. We're more like the bottom part of this diagram, below the dotted line. Aura is running on Kubernetes infrastructure. And that's our kind of interface to the cloud world in general. Now, this has been pretty controversial in the past. I don't know whether people have heard this quote before. This is Kelsey Hightower over at Google. He said back in 2016, he said, if you do this, exactly what we're doing, you will lose your job. That's pretty that should make you stop and think for a moment if you've got somebody saying something like that. And this was quite widely reported at the time. What I can say is that Kelsey's changed his mind since then publicly, and it's mostly because Kubernetes has moved on a great deal since then. But also, there are things that you need. So there was the things that are still true about his reasoning. It's a big undertaking to run on Kubernetes and to get it right, to get the kind of reliability and data durability that you need to run a database as a service. We're prepared to invest in that because we're a database company. But as a general choice, if you were just running any old piece of database software, it still might not be a good decision for you. We've got a strategy or approach for how we use Kubernetes. So first of all, we're using it for what it's really good at. And from my point of view, it's about managing the complexity of a pretty complicated infrastructure, all the different pieces that we need. Especially the declarative state mechanism makes it really easy to implement self-healing systems, which is exactly what we need in a very large deployment. When we go beyond what Kubernetes has built in, we're going to extend the service following the same patterns. So we're going to introduce our own resources, our own higher level resources, which are going to follow the same pattern and extend it cleanly. But the final point is that we don't delegate everything to the cloud platforms. There's some kind of capabilities that actually we're going to use the core capabilities in the database to provide. And that's especially the durability, the consistency elements that we're using in the core database. And we rely on the Raft protocol and that implementation to do that. Let's talk about what Raft is, because I've just explained it. So here's a little animation. I won't explain what's going on. But Raft is a distributed consensus protocol. The Neo4j database uses that protocol to safely replicate data in a consistent way around a cluster. And it's a really cool protocol. We've had it in Neo4j since 2016, so it's pretty battle tested by now, and it's a very solid way of operating. But you don't just get the consensus with Raft, you also get a pretty robust membership protocol. So it gives you the mechanisms to safely change the membership of the cluster without getting into a split brain situation or some kind of divergence of data. And that's a really powerful thing that we can lean on in the design of our database as a service. So let's take an example. here's a really straightforward 3-member cluster. Imagine we have this. Now, as is going to happen, from time to time, one of those members is likely to fail, something go wrong. Maybe a hardware failure, maybe some software abnormality of some kind. Built into Kubernetes, we have the capability to recognize that something is down, so to use availability metrics to remove a server from the load balancing. I colored it gray to indicate that. And we can also start up a new member to replace it. So here's a new member starting up, it's gray, and then it goes to the white state. Eventually, the damaged server is removed completely and shut down. It's important that we have the Raft protocol because otherwise something could really go wrong in this situation. We could easily start up with a new server with no data on it and have that as the master and lose all our data, something like that. And it's the Raft protocol that's helping us keep consistent in that state. For a more complicated example, so with this lump of circles, what we're doing here is we're scaling the servers from a 16 gigabyte size, that's a size, to a 32 gigabyte size. And we can have a protocol where we completely replace all of the hardware without any downtime for reads or writes. And we're able to do that because of the underlying protocol that's inside there. The third example is kind of interesting. It's exactly the same shape as the scaling example, but here we're upgrading the software. I've drawn this as V23, V24. What that's saying is a new version of the Neo4j database software. We need to take new versions for bug fixes or for security patches. We want to do that without any kind of downtime. We can do that because the database has been engineered to cooperate between adjacent versions, and we can upgrade without any interruption of service. Okay, so that's the process we're going to follow. How do we actually implement it in Kubernetes? Well, we're following the core. Kubernetes works on a core pattern we call Reconcile pattern. I've tried to draw a picture of it here. So you interface with the Reconcile pattern by writing a desired state into the system. And then you have a controller which compares that desired state with its perception, its measurement of the actual state of the system. In general, those are going to match. So this is on a constant loop, constantly checking. In general, it's in steady state, no actions are required. But sometimes there's a mismatch. And when there's a mismatch, the controller decides to take an action. And that action eventually leads to the actual state matching the desired state. This is the core way that Kubernetes is operating. As a slightly more concrete example, if we were trying to have a cluster with 3 members, on the left-hand side, there are 3 members, nothing to do. On the right-hand side, there are only 2. For some reason, whatever reason that is, the controller will take the action to add a new cluster member. This seems very simple, and that's for good reason. This is how Kubernetes is built up. It's built up in a layered architecture. So each controller, it often delegates to another resource type managed by another controller. So you end up with a kind of hierarchy. And this is what we do exactly in Neo4j. So we have something called the Neo4j operator. This is vastly simplified, but some of the Kubernetes resource it uses are a stateful set, a pod, lowest level Kubernetes resource, and a persistent volume. And we're following the same pattern that you get in core Kubernetes. So it's great we've got an operator now, but the next question is, where do we run this thing? Like, how are we going to structure the overall architecture? We're going to have like one operator and it's going to operate tens of thousands of databases, or is it one database and one controller? Basically what we're asking is, what is N in this picture? How many databases should we manage with a controller? And to kind of help us answer this question, we introduced a concept specific to Aura. We came up with this concept of Orchestra. And I hope this looks like an orchestra to you. An orchestra for us is our deployment of Kubernetes cluster divided into a control plane where the operator lives, and a data plane where all of the databases managed by that operator live. And And we also need some other services to make the whole thing work. But it's completely self-contained, it's isolated, independent, and yeah, it just keeps going in that way.
It's sleepy.
It's really, really sleepy. Okay, the advantages of this are that we have the isolation, I've already talked about that, but in terms of that number, what we can do is test with a certain number of databases, and we know that the Orchestra works to our acceptable characteristics with that number and that kind of load. If we want to scale, if we want to add more databases, we can add another whole Orchestra, another whole Kubernetes cluster, and that can take us up to a very large scale. It also gives us that cross-cloud capability that we can use this roughly as pattern. It needs customization, but roughly as pattern on each of the clouds. How many do we need of this? Well, the minimum we need is one Orchestra per combination of region and cloud provider. You'll see on this picture, it's kind of schematic, but you'll see that in some regions we have more. We're going to have more Orchestras, and that's going to be to do with demand. How many customers want to run their database in that particular Orchestra? So it sounds like we shouldn't have that many Orchestras, maybe like tens or hundreds of, how many regions are there? But actually, there's a bit more of a wrinkle in this because we talked right at the beginning of the challenges, customers have different needs. And particularly we have our enterprise customers who would really like the highest possible level of isolation from of their data from everything else. And that's why we actually implement a single tenant kind of system where we put an entire Orchestra. It's the same kind of concepts, the same capabilities, but we dedicate an Orchestra to an individual customer. And that means that, it's less efficient, so we charge more money for it because there's less sharing, but it means that we're actually running hundreds of Kubernetes clusters in production. And that's a really, like talking to other companies that use Kubernetes, that's a pretty high number actually of clusters in production. Okay, that was about the cloud section. Let's look at third-party services. So as a recap, there are some things that we definitely want to build ourselves. Obviously, the core data platform, the core database, we're going to build. A small example is the role-based access control. That's something that we use built into the core database. And then the consistency, replication, durability, that's obviously another thing that's in the core database. But there are some things that aren't really our business. They're not really what we're into. But they're still really important for providing the service. So the things that we delegate out, I've listed here some of those: authentication, billing. You kind of get the idea from the vendors that we're using at the moment, and this is not exhaustive, but these things that are out there that we're using as part of the live system. Especially, I just call out Datadog is a really big area for us. We're obviously with all of our monitoring and alerting, that's hugely important to Aura. We're using SNCC for analyzing our dependencies from a security perspective. And then we're actually, for our process point of view, we're using a tool called Athenian. And that's appropriate because now we're going to talk about process. So what are we doing in engineering? How do we think about developing a service like this? Well, first of all, really important to operating a service. It's very handy that our friends at Google wrote down a lot of stuff in this book and all the community around it. So in the site reliability engineering, having coined that is very helpful for us. There's a lot to say about SRE world. I'm just going to call out a couple of things that like my takeaways from it. So first of all, it's about how we think about errors and reliability and being data-driven in that area. So we talk about, in SRE world, we talk about error budgets and about making a decision about what to do based on how many errors have occurred during a certain period, doing some data-driven decision-making there. And this is a very simple model, just the idea that there's more, the faster you're having errors, the longer it takes, or the less time it takes for you to change your mind and take a different course of action. But there's one thing I should kind of, maybe people are kind of ringing alarm bells. Think it's a database as a service. Why are we talking about errors? Surely, like, database service should be super reliable, super solid, never go wrong, right? That's what we expect. And yes, actually, Aura is super reliable and has great uptime. But there's actually a lot of stuff going on in there all the time. And I just want to, and maybe the key way to think about this is that we're offering a service on which people run their own code. It's like a whole nother level of noise compared to offering a service that just runs your one application. So in terms of monitoring what's going on, we have to think about what those users are doing. My favorite example I'm going to use here is to talk about syntax errors. So imagine this Cypher query. You probably recognize there's something wrong with it. There's a missing parenthesis. This can't be executed by the database. It's going to give an error. And we should be tracking those errors somewhere. But it's perfectly legitimate that a user can run a query like this. It's not a problem. It's not like our fault that it didn't work. It's their fault for writing the wrong query. But if we totally ignore this type of error, that's also a bad thing. Because that means that if there was some situation where suddenly we throw up a lot of syntax errors for incorrectly, we wouldn't catch that at all. So we need to think quite carefully about distinguishing between noise and genuine failure, something genuinely going wrong. And this leads us to much more complicated kind of ways of thinking about burn down rates and error alerting. So we end up with this very complicated picture I can't really explain, but this multi-window, multi-burn rates alerting, we get into that kind of world in SRE. The other thing I want to talk about in SRE is about what we do when something does happen, when we notice something in the chart, some piece of infrastructure that isn't working as we expect. We're getting metrics from our cloud infrastructure, from Kubernetes, and also from Neo4j Operator, which giving the user perspective on what's going wrong. All those are reporting metrics. Our alerts come off those metrics, and those are handled by our engineers. They use written down tools to automate that process, and they use playbooks so that we have a clear set of things to follow. It's great that we have this process all written, and we make it as slick as possible so that we can keep things running at a good level. But I think the really important thing actually is more the feedback cycle that comes out of this. So we go through a post-mortem process, and that hopefully allows us to fix the product. Or if not, that's not the right thing to do right now, then it's going to be improving the tools and the playbook so that we can recover more quickly from the situation or automate away the toil of recovery. So it's really the feedback loop that I think is really important here. Next thing I want to talk about on process is to talk about continuous delivery and this family of practices. So I want to say in Neo4j as a company, it's really been ingrained in us from a long time. I mean, I'm putting this book cover up here mostly for some nostalgia from working with Jez and Dave back 15 years ago, and a lot of it's come from that background of like the early days of back 20 years ago, early days of agile practices and following agile and working out what the agile principles should be, valuing working software over anything else. We're especially keen on testing and automated testing in Neo4j Engineering, and we automate aggressively. That's how I describe it. So I just want to, I've got a little model I've been playing with about the journey we've been through. You can think about software development in like 2 steps, if you like. You have to write the code, and you have to integrate it with the work of your colleagues. For the last 20 years, we've had the idea of continuous integration. We have the name of continuous integration for 20 years now. And that encourages us to go around this loop as quickly as possible and to take the smallest units of code and integration to write so that we can go faster. At Neo4j, for the most of our history, we've been releasing a packaged product. And that means that occasionally we branch off of this cycle and we make a release. But it's different when you're operating a service. In fact, instead, your graph looks more like this, your process looks more like this. There's a deploy stage that happens straight away after you've integrated. And that takes us into continuous deployment. This is the cycle that actually we want to be in a service world. And it's a very different world from where we were doing packaged software. It's actually each piece of code, we really want to get that all the way into production. And that's something we weren't able to do when we were releasing a packaged product. We've gone from just like this kind of impact of this. We were looking at releasing every 6 months of the core database. That was our kind of tempo. So if you wrote some code, that's how long it might be until it got to any customers at all. Now what we're aiming for with running a service is that it's possible to get code from being typed in into production in 15 minutes. That's our target. We have lots of mitigations and extra levels of control around this so that we can do that in a safe way. But that's certainly what we're aiming for. And it's made a big difference to us now that we're, rather than releasing every 6 months, I mean, I just looked at the stats before doing this, we're doing about 35 deploys to production per week at the moment. And our aspiration is to be much higher than that and to have lots more smaller units going out. But going back to this continuous deployment, it's all great to do things more frequently, but where are we really aiming for? Like, where's the goal of this? Well, really what we want to be getting to is continuous improvement. We want to be actually measuring the impact of the changes we put into production, analyzing and designing straight away the next piece of work that we do. And this is really the direction that we're heading in. Okay, so that was all the process stuff. So it's time to have a glimpse into the future, which obviously looks like a graph. There we go. A lot of this is roadmap stuff, and I'm not going to talk in detail about roadmap features at all. That's not the thing for this talk. But I'm sure you see that there's lots of data and tool integration. That's what I call it. There was some of that in Emil's keynote this morning about some of the exciting things happening there. More integrations with more platforms, more data integrations. I'm sure there'll also be a lot more deeper integration with the cloud platforms. I'm sure that's like at the data layer, but also at the infrastructure layer and the way that you pay for these services. I'm sure that's going to come as well. But finally, I think the thing that I'm really passionate about, especially, is the improvements to the core data platform, and that this is really the kind of proposition of Aura, is that this is the best graph platform, and it's all about making that graph part absolutely the best that it can be. So just thinking about that as a little example, the kind of things that we do in this space. Right now, users can write Cypher queries and they send them to Aura, to their application or through Neo4j browser. And they eventually find their way to a Neo4j database that executes those queries. What we're able to do, because we're operating this service, is we have the capability to take those same queries that are running on users' databases. We can aggressively anonymize them, that completely scrubs them of anything you could interpret. Any data or even variable names or anything, they go completely into an abstract sense. But it gives us enough of what people are doing in the database that we can put this into the same analytics engine, and we can work out what people are doing and make sure that our testing actually covers that stuff. So already we're starting to see, we're starting to find a few gaps in our benchmarking coverage that we couldn't have predicted, but we're finding that people are doing complicated, unexpected things in the database. We can make sure that we make those things go faster, and ultimately this is about making the database and the data platform much faster and I guess better in the long term. So this is really that's my glance into the future is this feedback cycle. So that was my kind of that was my like run through the 3 principles and then a little bit of a glance into the future. I'm just going to leave you with some like kind of a summary, like some takeaways from this. So how I would describe it is that Neo4j Aura is a fully managed service. We talked about that at the beginning. It runs on multiple clouds. On those clouds, it's running on Kubernetes, in fact, managed Kubernetes. And we're running hundreds of Kubernetes clusters. That's quite a big deal. And then us in Neo4j Engineering, we automate aggressively as part of our culture. We've implemented the data-driven SRE methods that we talked about a little bit before. And then finally, that we're the experts in graph. That's kind of the point. Is that's the thing that we're very good at, and we're going to continue to get better at through this mechanism. So that's it. Thank you very much. Great. I think I'm going to go outside in the corridor because I think we're a little over time, and I will take questions out there if that's okay. Everyone? Great. Thanks very much.